In this project, a biomimetic hummingbird flapping mechanism was designed using approximate spherical 4-bar synthesis. Hummingbirds use a unique flapping motion where a lift is produced during both the downstroke and the upstroke. This is accomplished by twisting their wing and creating a figure-8 motion. In this project, we wanted to replicate this wing motion using a spherical 4-bar mechanism. The spherical 4-bar is well suited for this task for many reasons. It produces motion on the surface of a sphere, and this has been found to approximate many biomimetic spatial motions. Additionally, the mechanism is only 1 degree of freedom, meaning only one motor is required. Since the motion is built directly into the kinematics, this motor can run at high speeds and produce a repetitive spatial motion without any position control. Here, we show the motion produced by a spherical 4-bar and its kinematic diagram. The goal of motion generation is to solve for the mechanism dimensions that approximate a specified motion. First, we specify task positions on a sphere by observing the flapping motion of a hummingbird. Then, we apply an optimization algorithm to find all candidate solutions that represent critical points of an objective function. These solutions can be parsed to find a mechanism with suitable characteristics. Here, solution 11 was selected since it approximates the motion well and avoids any defects or singularities. The mechanism was fabricated using a combination of aluminum tube, steel pins, and 3D printed plastic. For this prototype, actuation of one wing was produced externally by a brushless drill. To create the wing on the opposite side, the mechanism was flipped across the center plane of the hummingbird body. Using the drill, we were able to produce wing flapping at speeds up to 15 Hz. Real hummingbirds are able to flap their wings from 25 to 50 Hz, so this mechanism flaps slightly slower than a real hummingbird. This prototype is limited by material strength and fabrication robustness, so it is feasible that future versions could flap at the speeds of real hummingbirds. Compared to other flapping mechanisms, this spherical 4-bar is unique because it has a figure-8 motion built directly into its motion and only needs one motor. It also incorporates wing twisting without relying on a flexible membrane, which could improve aerodynamic performance. Possible applications of this mechanism include small-scale UAVs for surveillance, as well as UAVs with quieter flights than traditional propellers. This mechanism could also be used to study the dynamics of hummingbird flight without relying solely on biological data measurement. In the future work of this project, the design will be updated to more closely approximate real hummingbird kinematics data collected by biologists. Updates will then be made to the prototype, including implementing a motor, battery, and other electronics, and reducing weight and size to produce real flight. Thank you to the ASME SMRDC committee for setting up this competition, and thank you for watching this presentation.